Hello, Burkhart. I'm going to try to make an answer key for this. So here we go. Number one, there's a ball and a string. It's going around like this. Woo 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 woo. Like woo woo. What point P? Draw a free body diagram for the ball when is it at point P. So there's force gravity here, and then there's a string tied to it right here. And we can just pretend like there's no air, because who cares? So which way is the string pulling? Which way is the tension? Well, I would say it's this way. That would be a tension force. And that tension is causing a centripetal force, but you don't ever put a centripetal force in your free body diagram. Can you think of any other forces? Please let me know. I don't see a normal force because and we said the air didn't matter, so you could put maybe a little air friction pointing up on it, I guess, if you wanted to. Now here's a tricky problem that some people had a problem with. The car is traveling at a constant speed and makes a turn. So basically from the top view, the car is turning like this, right? And the radius of the turn is 60 meters. And its speed is 25. The minimum coefficient of friction needed to keep the car traveling along the path. So as the car travels along this path, right, we can see there's a free body diagram here, and the force of friction, so there's a centripetal force created anytime anything goes in a circle. The centripetal force is created anytime there's a circular path. Well, it's the force of friction which is creating that centripetal force, and if the friction wasn't great enough, the car would just slide sideways off the road. So what we need to do is we need to say, okay, the force of friction is equal to the centripetal force. And then we go find the formulas for those things. So the force of friction is equal to mu times the normal force. And that's equal to the centripetal force, which is mass times acceleration. And centripetal acceleration is v squared over r. And I'm just really hoping that the Khan Academy people explain that really well to you, because I never did. I really hope so. So mu is times mg. So the normal force and the force of gravity were equal to each other here, right? Because the car's not moving up and down in the vertical direction, equal to mv squared over r. So the mass cancels. I'm going to move over here. So I ran out of room. So mu is what we're looking for, right? The minimum coefficient of friction. The coefficient of friction is a physical property between two surfaces that determine how sticky they are, right? So basically, mu is equal to v squared over gr. So mu is equal to 25 squared divided by g, which we can just round off to 10 instead of 9.8. And I think that was 60. Hey, why don't you do the calculation and let me know how it turned out. All right, number 3, a ball is attached to a light string. It's swung in a circle on a turntable, so it's spinning around kind of horizontally. And there is this, so this is taking you to the gizmo, which I believe you all have a login for. I'm hoping so. Nobody asked me for the login. Maybe nobody needed it. I don't even know if I need to go play with this gizmo to figure this out, because I know that centripetal force is basically equal to mass times centripetal acceleration. So what happens if I increase the mass? Well, if I increase the mass, the centripetal force increases. If the velocity is decreased, right, this centripetal force decreases. If the radius is decreased, that's decreasing a denominator, which makes the centripetal force increase. Which will affect the centripetal force more, the speed or the radius? Well, the speed will, because it's squared. You're squaring something that's changing, and that's going to have a bigger effect than just changing something without squaring it. Number 4, astronauts in space shuttle experience weightlessness. Does this mean there is no gravity in space? The short answer is no, because Okay, so I know for a fact that the Khan Academy dude really spent a ton of time explaining this to you. Okay, but just to quickly review, your weight, mg, is the force of gravity. And the force of gravity, according to Newton, is the universal gravitational constant times the mass of you divided by the mass of the planet you're on, so that would be the Earth, divided by your distance squared, right? So your mass cancels. So the acceleration due to gravity anywhere near the Earth, including the space shuttle or space station or whatever space thing it is, the acceleration due to gravity that things would have there would be equal to the universal constant times the mass of the planet, which is the Earth, divided how far apart they are. So you can look these values up. You can go look up the mass of the Earth on the Google, and you can look up how far away the space shuttle orbits. If you add the distance of the space shuttle up into outer space to the radius of the planet, it doesn't really add a whole lot. And you will come up with the acceleration due to gravity a little less than 9. So they're not, that doesn't mean there's no, so they're weightless because they're in free fall. And please go back to Khan Academy and watch the video because they spent a lot of time explaining that. I know. All right, number 5, the true false questions. Okay, long story short, they're all false. There's no gravity in outer space. Just went over that. Yeah, there's gravity. There's gravity everywhere. Because gravity is, force of gravity, again, is equal to the product of any two masses in the universe divided by how far apart they are, their centers are. And then to make it all equal, we have this universal law of gravitation fudge factor physical constant, which is 6.7 times 10 to the negative 11. Very, very small. And that's why the force of gravity is so small. But if there are two masses, then there's a force of gravity between them. Any two masses in the universe will experience a force of gravity between them no matter what, no matter where they are. It'll be very, very small. But it's there. So there's gravity in outer space. Newton discovered gravity. That's ridiculous. He came up with an elegant explanation of how to determine the force of gravity using calculus. It was beautiful. But he was standing on the shoulders of people like Galileo. There were plenty of people who knew about gravity. Gravity was an idea that existed long before Newton wrote his books and came up with his ideas. The Earth's gravity does not extend to the outer planets. Okay, we just explained that. That's false. There's this planet and that planet, and according to this formula, they will experience a force of gravity between them no matter what. It's a small amount, perhaps, but it's there. The force of Earth's gravity on objects in orbit is near zero. Still false. Then E is just some random weird question about, this is like an astronomy question. The crescent shape of the moon is caused by the Earth's shadow. No. And really, normally at this point, I would pull out a globe and I would pull out my little baseball that I have Darth Vader's face on, and we would walk you through the phases of the moon and how the phases of the moon are created. But they basically have nothing really to do with the Earth's shadow. The Earth's shadow does create eclipses on the moon, lunar eclipses, but that's it. And because of the wobbliness of the orbits, you don't get an eclipse every time it goes around. But the phases of the moon are caused by the fact that, anyways, you know what, it would be better for me to go find it, to make a whole video about that if people care and explain it, because I certainly can explain it, or to go find some other dude who explained it and show you that video, whatever. Or you could just go to YouTube and say, type in, explain the phases of the moon to me, and then there's probably 50 people on there already who can explain them to you. Anyways, that was way too much time spent on that. All right, so F, the pull of the moon's gravity causes tides. Okay, that statement is true. The pull of the sun does not cause any significant tides. That is probably true. I think it's true. It sounds true. Therefore, the moon exerts a larger force on the Earth than does the sun. Now, I'm sure that's false. Using the force of gravity formula, if you put in the mass of the Earth and the mass of the sun, divided by the distance between them, you'll get a number. And then if you put in the mass of the Earth and the mass of the Moon and the distance between them, you'll get a number. And what you'll find is the sun number is way bigger. You know why? Because the sun is enormous. It's mind-bogglingly enormous. You cannot even imagine how big the sun is. And yeah, that distance is big too, but you're going to get a big force of gravity. So how come the sun doesn't cause significant tides? I don't really know. I would have to Google that personally. I'm sorry. It's not really on topic though. So Jupiter has a mass 300 times bigger than the Earth's mass, so you should weigh 300 times more. Nope, and it's because the weight here for you is equal to, okay, big G is the same everywhere in the universe, and then there's your mass, that doesn't change. So now the Jupiter mass is 300 times bigger than the Earth's mass. Okay, so we put a 300 there, but the radius of Jupiter, right, is a lot. So I don't know what it is, but the radius of Jupiter is much, much bigger than the radius of the Earth. And we're going to square that. And so that's going to have an effect on your weight on the so-called surface of Jupiter, which doesn't exist because it's a gas giant, but whatever. So it's going to cause the actual force of gravity to only be 3 times your weight here instead of 300 times. All right, here is something that's really hard to read. So, you know, this seemed to me as I think I got this question off of the College Board website. I was looking like stuff for you to do, and I wanted to try to use some of the resources. And, you know, honestly, this is more of a big old review problem for uniform acceleration. So let's just go through it real quick. So the car races 50 meters, and we want to calculate the acceleration of the car during 50 meters. So the acceleration is what I want to know, and the displacement is 50, and I need some more information. Blah, 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 blah. There's a stop sign. Your assumed mass, that doesn't help. Speed, okay, so the speed when it gets to the end is 17, and I think we can assume that the car starts from rest. I'm doing it anyways. I'm going for it. So we have these variables. We got to pick a formula. I think it's this one, v squared equals v naught squared plus 2ax, because that's the right variables. So 17 squared equals, okay, that goes away. 2 times a times 50. Oof, handwriting is rough. So basically 17 squared divided by 100. Okay, I'll let you do that. The time it takes the car to reach the beginning of the hill. Okay, now let's add a t. So now we have our variables, and we could use any of the equations really to solve this as long as it has t in it. But I'm going to go with x equals 1/2. Oh, look at the handwriting's getting better. V naught plus vf times t, and solve for t. So that would be 50. The reason I picked that one is because it doesn't introduce the acceleration that was. What if I calculated the acceleration wrong? Then I would get this one wrong too. So I'm going to just use the given information. So that's 100 divided by 17. You do the algebra, multiply both sides by 2. That makes it 100 divided by 17. The time is equal to 100 divided by 17. And the magnitude of the net force required to accelerate the car would be equal to ma. So the net force would be equal to 1600 times your answer for part A, which is acceleration, which was 17 squared divided by 100, right? That's what goes there. I'm not doing it. On the dot that represents the car, draw and label the forces that act on the car at the top of the hill but travels over the hill without losing contact. All right, so let's just move our drawing over here. So we're at the top of the hill. There's going to be a force of gravity at the top of the hill, and then there's going to be a normal force. And the normal, so here's the part where it actually is relative to our lesson. The normal force is not going to be the same as the force of gravity. And I think it's going to be actually less than the force of gravity, because as you roll up that hill, you will experience a little bit of lift due to the fact that you're zooming up a hill. And if you've ever driven over a hill like that, you know what I'm talking about. Your tummy drops out and you go, woo! Right? And you try that sometime, try driving. at a significant but not dangerous rate of speed over a bump or a hill, and you will feel you'll feel like you're in a little bit of free fall as you go over it. That means the normal force is less because the ground isn't supporting all of our weight anymore because we're getting some lift from zooming over the hill. All right, our last question today. These clever people have a block and they're rotating it and they're collecting this v-squared data and the radius data. And that has something to do with centripetal something something because those are our values. Those are our things for centripetal something something. So what is right? So if I draw a line there, what's the slope of the line mean? And okay, so during the experiment, blah, 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 blah. So basically, again, going back to our other problem, the coefficient of friction times mg is equal to the centripetal force. Mass cancels, so so basically what you have here is you have mu gr equals v squared. So that is like a formula like y equals mx plus b. Well, b is 0, right here, right? Because if there's 0 v, there's 0 r. So we can just, right? So y equals mx. So v squared is on the y-axis, and r is on the x-axis. So the slope is mu g. So if I want to figure out what the coefficient of friction is, I got to find the slope of the line, of the best fit line. So that's basically the first thing is to realize is you got to use the slope of a line. That's the best way to do science. You collect data, you draw a best fit line, and you find the slope of the line if it's linear. And so it has to be A or B. So C and D are both not good answers because they're not really using a good methodology. Their methodology is flawed. They're just using one data point. C, you're using one data point, which is the maximum value, and in D, you're using the midpoint or average one, but still, that's really not, that's not good method. You need to use all of the data, and to use all of the data, you need to find the slope of a line. So we find the slope of a line. The slope of the line then is equal to USG. It's right there. So the answer was B. And this is a blank page, and this is a blank page, and this is a knock-knock joke. All right, that's it. We're done. And I'm going to post this to the YouTube right now, and then I'm going to delay its publication until midnight tonight, and then you can go watch it.